So, welcome to this new lecture again. And today, in this lecture, we will not be talking about something new. Rather, this lecture will particularly play a role of a check post, And it's like here we will do recap of what we did in the last few lectures, like maybe 10 lectures, past 10 lectures. And so, we we started with a concept of algebraic structure, right? And we saw different kind of structure, and we started with a simple magma, and then we started adding axioms on top of it, and we continued the process of creation of new kind of algebraic structure, if you say. And we got semi group, we got monoid, we got group, we got abelian group, right? And then from there we started to generalize the very concept of what algebraic structure could be, right? And we saw ring, and then we saw field, and then we extended further, and then we delve into quite deeply into the idea of action structure, like action, a set we had and another set we had, and both had one set had it was a set of operators, and the other set was some set of polynomials, and this set was acting on this set, right? And we said it has identity, one way identity, and then it has it satisfies closure property, and we said it is monoid with a very particular kind of identity, right? We also checked associativity and commutativity, but it failed, right? Maybe you people were wondering about last two lectures why I was trying so hard to check associativity property of that action kind of structure. Well, the reason is I wanted to show that how mathematics evolves, I know the last few lecture, one or two, it was quite fast, and it was quite doodling and all kind of stops, and I never like those kind of, I never like that way of teaching, but it escalated into very different kind of, yes, and but from now on, I am not going to do that kind of stuff. I mean, doodling kind of stuff. That was a live construction of the structure we were doing. I was not prepared, and I'm sorry for that. And I was not prepared, and also the reason for not being prepared for that particular lecture was because I wanted to show a live process of how mathematics work, and we were together building some structure, modifying, then going back and forth and adding different kind of operations, then finding loopholes in the definitions and all kind of stuff. These are the live process that I wanted to show you, right? But then I realized it was quite difficult to follow, so now from now on I promise that I won't do that kind of stuff. Anyway, last time we established that it fills associativity property because we checked those absolute value and all kind of stuffs, and they were not equal, so they were not associativity. But I have to say one more thing, that that was not only the reason why the associativity fails. The reason it failed is quite deeper than that. It was not because those absolute values were not equal. The reason is because we used two definitions of derivative operator, you see, and that was somehow sneaking behind our structure that we were trying to create. And like for example, our set has the operator identity, first derivative, second derivative, and third derivative, right? But you see, we defined dy dx acting on, let's say, d square upon dx square, and we said the answer should be absolute value of the difference between their powers, the order of the derivative. But if see, this is a problem. Why this is a problem? Because what d square by dx square means? Well, it means d by dx of d by dx, isn't it? But here we are using a different kind of definition of what could d square by dx square means. It could mean absolute value of 1 minus 3, it could mean absolute value of 3 minus 1. So that is the problem. We were mixing two different kind of scenario into this, and that was the mistake, you see. So that is the homework. If you can see what's happening there and check yourself if you can find such operation where this associativity for that kind of a structure holds or not, right? Now we are gonna recap and a few things that we talked last time, and that is algebraic structure. Two different paths we took. The one algebraic structure was going in the direction of operations, and the other was going in the direction of actions. And we said we maybe combine these two ideas into one algebraic structure, operation and action going on. And we said this kind of new structure can evolve. What I mean is, maybe I can show you here on the picture. So what I'm trying to say that last time what we did, the recap, a little bit recap. So we had a set S, and on this set we try to put an operation S comma, let's say star, and it formed an algebraic structure. This is an algebraic structure. And then we said we can extend it further, star, and maybe add two operation in this, right? Two operation, and it become a different kind of a structure. Then we said why stop at 2? Maybe we can add 3, right? And we get this kind of a structure, a set and 3 operation on this. And we can go further extending this, and we can say a set and many operations, multi operations, star n, up to star n, right? So this was one path we chose, right? And so this is our first path. Let me draw the path here. The path is this way, right? So this is one path that we are choosing, right? And this is about operations and all, right? Now we chose different path, and we spent lot of time in this kind of a structure where we have two set and one operation, and we spend lot of time deciding what kind of structure this could be, right? And we said this is like action happening, right? And then we said we can extend it further, and that could be, let's say, why just two set and one operation? Why not 3 set and an operation, right? And then we said maybe we could do it further. Well, we can. Why not? Nothing stops us now. So maybe let's say we have n number of set up to Sn. There are n number of set. All set could be different, and they are different. And then an operation, right? So this path is different, right? Here we can see in this path, let's say we call it path P1. This is our path P2. So in the path 1, we see in all of these there is just one set, right? One set. Number of operations are changing, right? Number of operations are changing. Here we have one operation in all of them, just one operation. You can see number of set are changing, right? The most simplest kind of algebraic structure is this, which is set, just a set, right? Then we said this path P1 is about action, right? It's like action, something acting on something, right? And we said this here is about operation. By operation we mean algebra and all kind of stuff, arithmetic kind of things. So we have two different paths, and then we said why not mix these two idea, and we said let's mix it, and if we mix them together we got a third kind of idea where we have many set and many operation and we put together, so we get a many set up to Sn, and then there are also many operation star 1 star 2 star 3 star n, right? So we are combining. So this structure is, it's like it could be action plus operation, right? So this is our this is what algebraic structure look likes, right? And these operations, it could be binary, it could be unary, right? There are so many examples. The examples of unary operation is not get, right? We saw last time what is not get. Maybe I should tell a little bit about not operation. What is binary operation? We said binary operation is like a star that is gonna take two set S cross S. It takes two element and produces a single element. Like from S it's gonna choose A, from S it's gonna choose B, and then it's gonna operate on this and we get A star B. So a star is taking two element. It needs two element to work. That is called binary. Binary means two, and it produces some element. Now it is not necessary that this operations should be binary. No, these operations could be unary, it could be trinary, right? It could take three element, it could take one element, or it could take zero element, right? Zero array. The example of taking just one element is not operation, not, or we say it is in logic not, in set theory we say it is complement, right? What does it do? Well, let's say we have set b equal to 0 1 binary number, then this not operation is gonna take b to b only. This is unary, this is binary. Take S cross S, two set. Here is just one set, b to b. For example, let's choose b, from b one element. b is 0 and 1. Let's choose any one of this. So let's say b is 0. So what this not gonna do on the 0? Well, it says not of 0, and not of 0 is 1 by definition. It is going to flip the bit. So you see, a not is taking just one element to function. It's a different kind of operation. It's not binary, it's unary, right? What if we chose 0? The only option is now 1. If we choose 1, what it is gonna do? This not operation is going to act on 1 and it's going to produce the opposite of this bit, which is 0. It's a flipping bit. It's going to flip the data, right? So we have to remember that algebraic structure, in the definition we mostly say it should be binary, but that is not necessary at all. It could be any array. Any array means it could take one input, it could take two input, it could take three input, right? The operation is not limited to binary. Even in this, doesn't matter which path you choose. So this was algebraic structure, right? Now, so this is algebraic structure. Let me write top of it. It's an algebraic structure, right? Now, after studying algebraic structure, we're gonna talk a little bit about relational structure, right? Relational structure. What is it? Relational structure. We said in the past few lectures, mathematics is a study of abstract structure, and we also said structure are of two types, and we said they are algebraic structure, and then we said they are relational structure, right? And we studied algebraic structure quite deeply. Now our time is to study relational structure. But before that, what is the objective of this series? What is the objective of this series? A foundation of mathematics and philosophy. Well, the objective is we are going to find a theory on top of which our whole structure are built upon, right? We are going to find that theory, and this is the path I am taking. Okay, this is the path I am taking, the path of structure, algebraic structure. Some people take the traditional path is set theory. They start with set theory, and that is fine. Everyone has different kind of choice. It's called Zermelo-Fraenkel set theory, ZFC. C is about well, it's not necessary to tell right now, but it's exam of choice. So there is a set theory developed by these two people, Zermelo and Fraenkel, and they developed this idea of ZFC. And but before that, set theory was actually developed by Georg Cantor, right? And from there the whole story started, and later the set theory got its foundation quite like religion like following, and everybody started to use set theory to write whole mathematics. Even you can see here all the structure are written in the language of sets. These are all sets, and from set we are building every kind of a structure, right? All the language is set. So this path mostly people choose for foundation of mathematics, but we are choosing algebraic structure or simply structure. It could be relational, and from there we are trying to build everything, and later we will see that these all algebraic structure fall into a different kind of group. And I just want to do a little foreshadow, and the foreshadowing is that all the algebraic structure will be related to a theory called category theory. So we are building the whole idea for category theory. We are not taking the path of set theory. That is why I didn't started with set theory, right? I assume that we know everyone knows set theory because we have studied this since fourth grade. We have basic understanding of what set theory is. But if it will get necessary, I will give in between some ideas of what is set theory, right? But this is not important right now. So this is our objectives, that we will start with this algebraic structure, and we will build up to the until we reach category theory, right? And maybe we can extend this further and see where it goes, right? So this is the objective, and this lecture was just simply about recap what we did. That's all. So thank you for listening. Meet you in the next lecture.